just to kind of review, tomorrow I have another warm-up planned. It's in that same section of notes. Like I guess if you wanted to try it on your own first, you can. But we'll do this as a warm-up tomorrow. I like this one because it combines both integration by parts with the improper integrals. But today I did want to go ahead and move into some new stuff. And we are going to be looking at something called the second fundamental theorem of calculus. So we learned the first fundamental theorem of calculus, and the first FTC basically involves around how we evaluate a definite integral. The second FTC deals with taking the derivative of integrals. And what I mean by that, before we get into the second fundamental theorem of calculus, I want to talk about integral defined functions. So in math, we have looked at functions forever. Like we have f of x is equal to quadratics, f of x could be trig, f of x could be exponential, etc. All the different functions that we have. We can also create functions where they are actually a function of an integral. We will often call these integral defined functions. Which is what College Board kind of calls them whenever they are like listing out the topics that a teacher is supposed to teach. I learned them by calling them accumulation functions. And I kind of prefer that name for them because they better and more closely show like what that function actually represents. So how I would interpret this function is pretty intuitive. So this is the function g of x. And we know that this g of x is the integral from 2 to x of some other function. So basically g is an integral, and the integral is another function. Just notation-wise, do notice that those are different variables. And that's how we're always going to write our integral defined functions, just to kind of keep things separately. Like that 3t squared, like it doesn't really matter too much that's a t, but we do want it to be different from the x just to kind of show that g is the integral and we're taking the integral of this other function 3t squared. We often use t to represent time, also kind of connects back to like parametric functions in some way, but that part isn't really what's a major idea. The major idea is I call this an accumulation function because you think about it, we know the definite integral represents area under a curve. So we can kind of interpret this function as the area under the curve starting at 2 and then at various values of x. So like as x increases, maybe the area is accumulating, whether positive or negative, we're like adding up this area as we kind of go along. So these first 3 examples are honestly pretty straightforward. Like we know that when we see function notation, that tells us to plug in the number that we see in for x. So like when I see g of 3, that literally means, hey, whatever x is, replace it with a 3. So g of 3 in this case would just be the integral. The bottom part's not changing. It's always going to be 2, but we're going from 2 to 3 of 3t squared dt. And then we would just be able to evaluate that like a regular integral. The antiderivative of 3t squared is t cubed, and we're evaluating that from 2 to 3, and then plug in the top number minus plugging in the bottom number. And of course, we leave it unsimplified like that. Some things we will notice and kind of make sense. Like this is g of 2. This would literally mean 2. Well, x is 2, so the integral from 2 to 2. Wouldn't need to waste our time evaluating this one, because if I start at 2 and end at 2, I haven't gone anywhere, so I haven't been able to accumulate any area. So we know automatically that this one would be 0. Conceptually, we can interpret this as no net area. It also works when we're kind of moving backwards. So like this is g of 1. So we're still starting at 2, but I'm plugging in 1. Yes, those are backwards, but we know conceptually that's just going to like change the sign of the area. But we can evaluate it the normal way, t cubed from 2 to 1, and then plug in the top number minus the bottom number. That's pretty easy to simplify. 1 minus 8, -7. So that's what I mean by an integral defined function. We can write all sorts of integral defined functions. In fact, the whole second half of this unit deals with like different word problems of like modeling situations with these integral defined functions. So I'm calling these functions for a reason, because we can basically analyze them like we would any normal function. So we can do things like find the derivative of them, which is what we're going to focus on today, but we can also like integrate them. We can use them to solve problems. Anything we can do with a regular function, we can do with these integral defined functions. The second FTC informs us how we take the derivative of an integral as a function. Instead of just giving you the formula, I do want to kind of show you where it comes from. I think that will help you remember it. It is like a formula, but I do think it's pretty easy to see where it comes from. So I have this same integral defined function of g of x, and I ultimately want to use this g of x. Again, g is a function. I want to be able to find g prime. So I basically ultimately want to find the derivative of an integral. And conceptually, I think many of you can kind of imagine where this is headed. In math, we know that opposites kind of cancel each other out. Like a square root cancels out an x squared, a log would cancel out an exponent, plus cancel out a minus sign. Opposite operations tend to cancel out. Do need to treat this a little bit differently, but we can kind of see where this derivative is coming from by doing what I have as this like intermediate step of find a formula for g of x that does not use the integral symbol. And what I mean by that, if this is g of x, we know how to evaluate integrals to write an equivalent function that doesn't have an integral sign. So we know when we're evaluating an integral, we can go ahead and find the antiderivative. The antiderivative of 3t squared would be t cubed, top and bottom number. And then we evaluate it by plugging in the top number minus plugging in the bottom number. And I'm just going to write this as x cubed minus 8. So to be clear on what we have found, this integral that is an integral defined function is exactly the same thing as this function. So from that logic, the derivative of that function would equal the derivative of that integral. What's the derivative of that function? 3x squared. 8's a constant, so it would go to 0. So likewise, what's the derivative of this integral? The derivative of this integral would just be 3x squared. And I hope you can kind of see the very, very, very close relationship with this. We were integrating something that was 3t squared. In many ways, the derivative canceled out the integral sign, and what we're left with but 3x squared. And we would write that as 3x squared as opposed to 3t squared. We'll be able to make shortcuts and skip this intermediate step by using what's called the second fundamental theorem of calculus. And this second line right here is basically showing us an example of the second FTC. So I'm going to give it to you as a formula, and then we'll look at some examples. I'm going to call this the common case of the FTC. We'll look at two cases. We'll have the common case, and then we will have the general case. So the main idea behind the second FTC is how we take the derivative of integrals themselves. The common case is only going to be used in very, very specific situations. They will be used when the upper limit of integration is just x, not x squared, not 2x, not sine of x, but just x. And the lower limit of integration is just a constant. If you don't have those kind of qualities, then you are going to use what's called the general case. But the second FTC basically states that differentiation and integration are opposites. And if they are opposites, then they basically are going to cancel each other out. Well, how to express that? we would say that the derivative of the integral from a to x of f of t dt would just be equal to f of x, which is what we saw on the previous slide, where that like everything else kind of canceled and would end up with just what was on the inside of that integral. Not going to worry about the quick proof since we did see the example of why that worked on the previous slide. Questions so far before I show you an example? All right, so let's look at an example. I'm going to skip 2 slides ahead. Actually, no, it's 4 slides ahead, one that says analytically examples. There's 3 of them on the slide. We're just going to worry about the one that right now shows the common case, which is the very first example. So what this is, if you're looking at it, we're taking the derivative of an integral. Mathematically, we know that a derivative and an integral in many ways cancel out. Weird things happen, like we know we're plugging in the top minus the bottom, so to be careful and not just say that they directly cancel out. And that's where the second FTC is going to come from. This first one is going to use the common case. And I know it's going to use the common case because we just have a constant on the bottom and the upper limit of integration is x. So when I take the derivative of this integral, the common case is nice. Literally, the integral sign just cancels out. And this would just be equal to the square root of x. Why is this useful? Anything that we have done with the derivative, we can also do with these integral defined functions. So we can do things like tangent lines. We can do things like intervals of increasing and decreasing. We can talk about concavity. We can do relative extrema. We can do absolute extrema. That's not an exhaustive list. Anything we've done with the derivative from first semester, we can now do with these integral defined functions because we now know how to take the derivative of those functions. Questions about the common case of the second FTC? All right, so that's the common case. More important, we also have what's called the general case. The general case is going to be used when you don't have a constant as that lower limit of integration, and the upper limit of integration is not just x. So like looking at this one, we have a 5x and a tangent of x. I know it looks crazy to have like this integral sign with actual functions on the integral sign, but this is where the second FTC is going to be useful for us. Again, the ultimate goal when we're doing these problems is if I give you an integral defined functions, you can jump immediately to find the first derivative without having to rewrite it first. We're going to rewrite it first just to kind of see where it comes from, and then we'll use the formula and then some examples. So if this is my g, if I want to get rid of that integral, I have my antiderivative plugging in the top number minus plugging in the bottom number. In this case, those numbers are actual functions. So I have tangent of x plugging in the top cubed minus 5x cubed plugging in the bottom. Taking the derivative of this is the tangent cube, so I'm going to use the chain rule. So I'm going to have 3 tangent of x squared, what's the derivative of tangent, secant squared of x, minus, I know I can write that 5x by distributing the cube. I'm going to do the chain rule just to kind of see the pattern. 3 comes down in front, 5x squared times the derivative of 5x, which is 5. So we do see this chain rule action happening. There wasn't like a constant there, so that last term didn't cancel out completely, but that would be g prime of x. Patterns I want you to notice before I kind of change it and just give you the formula. We were taking the derivative of an integral that had 3t squared in it, and you can kind of see 3 something squared built into the problem. That still shows up when we took the derivative. That minus sign is coming from the first FTC because we do have the top minus the bottom, and then we also have the chain rule applying as well. This is going to be the general case for the FTC is again going to be used whenever you don't have just a number and x on the integral sign. To write this as a formula, the general case, again, the second FTC tells us how to take the derivative of an integral. I used u and v on here to show that those are more than just a constant and more than just x. So like u and v actually represent functions. In words, how I actually do this, we still have the first FTC. I think of it as plug in the top times its derivative. So the derivative of what you plugged in. And that's coming from the chain rule. And then minus, because we know that we're still using the first FTC, plug in the bottom times its derivative. Notation-wise, again, conceptually, we know the derivative and the integral are going to cancel each other out. So we're going to have plugging in the top minus plugging in the bottom, but we are taking the derivative, so we're still going to have to follow the chain rule. So there's the notation of what that in words is going to represent. Not going to worry about a quick proof because we saw an example of why that works out. But it's kind of combining this idea of how we evaluate definite integrals with the chain rule, since we are in some ways taking the derivative. Questions on that formula? Before we do examples, I do want to say some students just like doing the general case 100% of the time. The common case we know only works for a very specific example. The general case can really work for all examples, including the common ones. So here is the common case. We just have an x and a constant on the integral sign. If you're doing the general case, so again, you would plug in the top times the derivative of what you plugged in minus plugging in the bottom times the derivative of what you plugged in. Well, if a is a constant, its derivative is going to be 0. And we're still going to end up with f of x, which is what the common case of the second FTC tells us would happen. So look at some examples. I'm going to redo that first example, but use the general case. And then we have two follow-up ones that we can only use the general case for. So this first one, if I didn't want to use the common case, using the general case, plugging in the top times the derivative of what I plugged in, minus plugging in the bottom times the derivative of what I plugged in, which is clearly equal to the same thing, the square root of x. Looking at this second one, so again, I cannot use the common case. We're going to be forced to use the general case because we have an x squared, which is clearly not a constant, and a natural log of x, which is not just x. And again, the idea behind the second FTC is we're taking the derivative of an integral. Maybe we need to write the tangent line of this integral defined function, or maybe we need to find where this integral defined function has a horizontal tangent line. So taking its derivative, plug in the top, so that's going to become secant natural log of x tangent natural log of x times the derivative of what we plugged in, that's from the chain rule, minus plugging in the bottom, secant of x squared, tangent of x squared, then chain rule times the derivative of what we plugged in. That expression in red would be the derivative. If I said this integral defined function was, say, like h of x, what we have in red would be what h prime of x would be equal to. Questions or concerns so far? All right, last one. Pretty straightforward. So it looks like it's almost the common case. That x squared is kind of messing things up, so we will need to use the general case. We know conceptually the derivative of an integral will cancel each other out, but since we're taking the derivative, still need to worry about the chain rule, and how we evaluate definite integrals. So go ahead and plug in the top times the derivative of what you plugged in, so 2x, minus tangent plugging in the bottom times the derivative of what we just plugged in. The derivative of 3 is 0. So the derivative of this integral defined function is really just going to be a single term. Questions on doing the second FTC kind of algebraically? All right, so the next part of notes we're definitely not going to finish today, which is, I planned for that anyways, is from a handout I had. It's how we look at accumulation functions graphically. Questions like this are pretty much guaranteed on the AP exam. It's usually an entire question on the AB exam. On the BC exam, it's usually just part of a question. It's a good review of a lot of stuff we've done. So like how we analyze, like looking at a graph from the derivative, or looking at a graph, how can we interpret the derivative or the second derivative. I'm going to try to get numbers 1 and 2 done today, but we might just get 1 done so I don't have to rush too much. We'll just finish whatever we don't do tomorrow. So I do want us to pay attention to kind of what we have here. We have this function g of x, and g of x is this integral defined function. G of x, you can think of it as g of x is like this area of f of t. Whenever you look at an integral defined function, always some things you want to pay attention to. Determine if you're going to eventually use the common case or the generalized case. Looking at this one, we can tell that we are going to go ahead and use the common case. You also want to pay attention to where this integral is starting. We know that when we evaluate a definite integral, it is representing area. A lot of these are not going to be starting at 0, so you always want to kind of pay attention to where that integral is going to start at. And then we notice that this is the graph of f, not the graph of g. So we're going to use kind of the idea of like we have g of x, it's the integral of f, and then this is the graph of f for us to kind of use and answer our questions with. This first one is pretty straightforward. It's very similar to that very first slide we did today for the second FTC. Just doing function notation, if I see g of 3, that tells us to plug in 3 for x. So g of 3 literally means the integral from 1 to 3 of this function f. And we can find that using just regular geometry and area formulas. Again, we are starting at 1, and we are going to 3. And might divide it up into different shapes to find its area. What would its area be? We have 2 plus 4 plus going to be a 1. So it would have an area of 7. Looking at B, pretty easy as well. G of 1 means we're going to replace the x with a 1. Don't even need to look at the graph for this one. If I start at 1 and end at 1, there's no net area. So I know that the overall area would be 0. Do be careful, though, if your integral signs end up backwards. So this g of 0 would be the integral from 1 to 0 of f of t dt. Those are backwards, so we want to make sure we use the opposite sign of what we actually see on the graph. So from 0 to 1 itself, it has an area of 1/2 base times height, 1/2, 1 times 2, which is 1. We are moving backwards, though, so I do want to make sure I have a -1 as my answer. Questions on that? All right, let's go ahead and start number 2. Same graph, didn't want to change it, but now I'm going to ask for different things that we see. So we have g of x, and g of x is still that same 1 to x, didn't change that, still looking at the graph of f. But now I'm changing the question where we're going to find g of 6, g prime of 6, and g double prime of 6. Things that, of course, we're focusing on, g itself is an integral. So g of 6 is going to be the easiest one to find. That will be the integral from 1 to 6 of f of t dt. So we just want to find the area from 1 to 6. Still treat all your other rules the same. Like if you have negative area below the axis, make sure it is negative. We already found that the area from 1 to 3 is 7. So I'm looking at this, the area from 3 to 4, that's going to be 1/2, 1 times 4, which is 2. The area from 4 to 6, dividing it up, we are going to make sure that we see it's a negative area. So overall, what would g of 6 be? It's the net area from 1 to 6. So I have 7 plus 2 minus 1 minus 2, which is going to give me a net area of 6. Nothing there is really too new from what we've done. What will be new and where the second FTC is going to come from is when we have to find the derivative and the second derivative of this integral defined function. Well, if I know that g of x is this integral, I can use that to find g of x and g double prime of x. Again, we are using the common case. The lower limit of integration is a constant. The upper limit of integration is an x. So if I take the derivative of g, that integral sign will just cancel out. And we can see that g prime is literally the same thing as f of x. So in this problem that asked me to find g prime of 6, g prime of 6 is literally the same thing as f of 6. We know how to find f of 6. We can just read the graph. F of 6 is, right there, f of 6 is -2. We can continue that process. If g prime is f of x, then g double prime would be f prime of x. So if I want to find g double prime of 6, that's the same thing as saying f prime of 6. 6 on the graph is on this horizontal section. We know that f prime is basically the slope of a tangent line. We're not on a corner, so it's not undefined. That's a horizontal line. So its slope is going to be 0. So like looking and kind of comparing these, we see like this lagging thing of where like g is representing a net area, g prime is representing a value on the graph, g double prime is representing a slope on the graph. I know there's 10 minutes left of class, but I'm going to go ahead and stop there so we can finish everything else out tomorrow and not rush. Before you go, though, I did want to make sure I answered any questions about the second FTC. So go ahead. What are your questions, if you have any?
Can we do one where it's like not a graph and do a second?
Second derivative?
Yeah.
Yeah, so if you're finding a second derivative, I go back to this slide. I'll just make up one. If I let y be the integral from 3 to x of the square root of t dt. So like when you find the first derivative, that's going to use the second FTC. I conveniently chose one that would be the common case. So that would just be the square root of x. Once you get rid of that integral sign, you just find the derivative like you've always found the derivative. So there's no more integral signs. So like on this one, if I found the second derivative, it would just be 1/2 x to the -1/2. And you just treat it like a regular derivative once that integral sign goes away.
Okay, it's just normal. Got you. Thank you.
You're welcome. So the second FTC, to be clear, is only used when you're taking the derivative of an integral. Once that integral sign is gone, then it's just like what we did first semester. So we will finish it because, again, these graphical ones are important. I'm going to do the rest of these tomorrow. Your assignment that you can / should be working on If you're looking at the calendar, hopefully you finished homework 1 by now. If not, definitely finish that one up. Continue working on this homework number 2, which is the improper integrals. You can start homework 3. I would at least do, like, I have it divided into like a part 1, a part 2, and a part 3. I would at least do part 1. You might want to save the part 2 and 3 until we finish the notes. Again, most of you are smart enough to figure it out. No, not most. All of you are probably smart enough to look at figure it out, but don't want you to pile on too much at once. That's where we're at kind of right now. We're going to finish the FTC notes tomorrow. Wednesday is going to be just a work day. That, of course, is no longer returning face-to-face. But that first quiz over integration methods and the second FTC is going to be on Thursday. Do want to make sure it's on your radar as well. Starting Friday, you are going to want a graphing calculator. Obviously, I'm not at school right now, so there's no way for me to get a graphing calculator to you if you need one before Friday. But definitely please reach out to me as soon as possible if you will need me to loan you a graphing calculator for the rest of the semester, because we are going to start seeing more and more topics that we can't do without a graphing calculator. So with that being said, the live portion of class is over, and there's only like about 5 minutes to spare.